Hello, my friend. In the previous episode, we explored how tokenization works, how regular text is first transformed into binary numbers, made up of zeros and ones. Then we saw how this binary data is converted into decimal numbers, and finally how these numbers are mapped to symbols or tokens. As you may remember, this entire process helps us compress and structure the data, reducing the size of the sequence we work with. And now, in this episode, we'll use those tokenized sequences as input to a neural network, the next major step in how language models are trained. So, let's hand the mic over to Eva.
Thank you, Stephen. So what we have done so far is take a sequence of text, let's say in our example this text, and we represent it using our tokenizer, turning it into a sequence of tokens. And this is what it looks like now. If you refer back to dataset in the pre-training stage, you'll recall it takes up around 44 terabytes of disk space, and within it, there are roughly 15 trillion tokens. And I want from you to focus on this number. The few tokens you see here are just a tiny sample of the 15 trillion. Each token is like an atom in a language model. They may look like random numbers, but each one represents a unique ID mapped to a chunk of text. Now we reach the exciting part, neural network training. This is where the real computational heavy lifting happens. So, what exactly want to do here? We want the neural network to learn the statistical relationships between tokens. In other words, how likely it is that one token follows another. To do that, we take a window of tokens from the dataset. In this example, I'll take a window of 5 tokens. We will refer to this window of tokens as the context, and we feed it into the neural network. In real-world models, this window can range from a few tokens to something like 8,000 tokens, although longer windows require significantly more computational power. So remember, the input is a variable length sequence of tokens. We call it window. And here, let me slow down a bit. I really want you to focus on what I'm about to say. Let's take an example from a real-world scenario. Imagine you open a new chat with ChatGPT. You type a question, and ChatGPT gives you a reply. Let's say your question contains about 50 tokens. Not words, but tokens, which are usually smaller chunks like parts of words. Now, when you ask a new question in the same chat, ChatGPT doesn't just process your new question by itself. It reprocesses your previous question, its previous reply, and your new question together, as part of one bigger window. The model needs all that context to understand the conversation better. So every time you send a message, the amount of information inside the window grows. Your past messages and the model's responses are reprocessed to predict the next token. If the conversation gets really long and the number of tokens reaches the model's limit, like 8,000 or 32,000 tokens, the oldest parts of the conversation will start getting trimmed to make space for new messages, and so on. That's what we call a sliding window in action, and we will talk about it later.
Your example very wonderful, Eva. But wait a minute. I am really confusing about the number here. You previously said that if you go back to the FinWeb dataset, they mentioned that not only this 44 terabytes of disk space, but this is about a 15 trillion of token sequence in this dataset. So, from where you came this number 100,277? Sorry, but I really forget what you said in the previous episode.
No problem, Stephen. I liked when you asked question. I will give you a simple analogy to understand. Imagine a bag of 15 trillion colored beads, but they come from only 100,277 different colors. The model sees a lot of beads, but only from a fixed set of possible colors. As you can see in this picture, this collection of 15 trillion beads comes from these 100,277 original and unique beads. Just replace these beads with tokens, and you will get the idea. Well, let's continue. The neural network is initialized with random weights, which means that the probabilities it outputs at the very beginning of training are also kind of random, because it's a random transformation. Here we have 3 example predictions, but keep in mind that the network actually outputs around 100,277 numbers here, one for each token in the vocabulary. Right now, the neural network is saying that the token for 1122, which corresponding to a text somewhere has a 6% chance of coming next, and the token 2038, which also corresponding to a text somewhere has a 2% chance, and the probability of 279 has a 8% chance. But in our example, we already know the correct next token. It's token 279, because we sampled this window directly from the dataset. So now comes the important part. We apply a mathematical process that updates the neural network. We tune it so that the probability of the correct token becomes slightly higher. In our example, it's 279, and the probabilities of the incorrect tokens become slightly lower. After this update, if I feed the exact same sequence of tokens back into the neural network, it will now give a higher probability to token 279, the correct next token in this context. This updating process happens in parallel across massive batches of data, for millions of tokens at a time, and this is what we call training the neural network. Through countless updates like this, the network gradually learns to align its predictions with the actual statistical patterns found in the dataset, until its guesses start to match the structure of real language. So now, let me quickly explain what we've learned so far in this episode. First, we start with a huge dataset, around 44 terabytes of text, and split it into tiny pieces called tokens, words, subwords, or characters. The full dataset contains about 15 trillion tokens, but there are only 100,277 unique tokens, like having trillions of colored beads, but only a fixed number of colors. 2. We introduce the idea of a window, a small sequence of tokens that the model uses as context to predict what token comes next. 3. When you chat with models like ChatGPT, the model reprocesses the entire conversation history inside a window, up to 8,000 or 32,000 tokens, every time you send a new message. Or, at the start of training, the neural network's weights are random, so its first predictions are mostly random guesses. For every window of tokens, the model predicts the next token by assigning probabilities across all 100,277 possible tokens. 5. Since we know the correct next token, we adjust the model's internal settings, its weights, to increase the probability of the correct token and decrease the probability of the wrong ones. 6. This updating process happens millions of times across huge batches of data, slowly teaching the model the real statistical patterns of the language. In the end, the model becomes very good at predicting the next token based on the patterns it learned from all that training data. And that's it.
Thank you, Eva. You absolutely nailed it. I'm looking forward to the next part. Stay tuned.